I'm Karen Gundy-Burlett. I'm the program manager for the NAMS-2 contract here at NASA Ames, and I would like to welcome you to today's edition of Airtime by NAMS-2, presented by Crown Innovations in collaboration with UC's Citrus and Banatao Institute. This is a series of seminars on advanced aviation, interesting research, and innovative methodologies in AAM and air traffic management. And today's topic is hybrid systems methods for assured AI in advanced air mobility and autonomous aviation. And today's speaker, Ricardo Sanfelice, is professor and department chair of electrical and computer engineering at UC California at Santa Cruz. He is the recipient of the 2013 SIAM Control and Systems Theory Prize, the National Science Foundation Career Award, the Air Force Young Investigator Research Award, the 2010 IEEE Control Systems Magazine Outstanding Paper Award, and so many other awards and honors. So I'm going to cut that a little bit short, but you've got the idea. He is the director of the Cyber-Physical Systems Research Center at UCSC, and director of the Center for Information Technology Research in the interests of society and the Banatao Institute Aviation Initiative. Dr. Sanfelice.
Thank you very much for the introduction and the invitation, Karen and everyone. And it's great to be here in person. I haven't been to NASA Ames in a while, and it's great to see familiar faces here in the room. I will be talking about some of the work that I've been doing with my students, Jan de Pristen and Paul Wins, over the past 2 years. And this is very well connected to the purposes of NAMS-2. I'm very excited about this project to see how what we're doing at Santa Cruz and also Citrus Aviation can help move forward with the research. I'm particularly a control theory person, and much of the things that I'm going to present to you will be connections to applications, and the applications I'm excited about are listed in the title. But I will start by saying that I'll be talking about something called hybrid systems. These are not necessarily hybrid vehicles, but they could be connected to technology within hybrid vehicles. A hybrid system is, in my perspective, is a dynamical feature, is whether the system has different type of behavior corresponding to how the variables of the system evolve. And this slide here that I have kind of shows kind of the classes of systems that if you're familiar with modeling that might emerge. The first class is what's called a switch system, where you have a variable called Z that captures basically position, velocity, orientation, and whatnot. That variable changes over time, let's say continuously, and it changes according to a function that depends on a switching signal. So whether the switching signal is 0, 1, 2, or 3, you might have different type of motion for this variable Z over time. You can also think about situations that are more dramatic, where the state is not only changing continuously, but also at certain times, let's say T1, T2, and so on, which we call event times, the state of the system, the variables of the system change abruptly to a new value. Okay? And this will be important in situations like you see right here, where you have a hybrid automata type of system, where you might have a system where you have it operating in different stages or different phases of its evolution, like for an aircraft, it would be taxiing, takeoff, cruise, landing, avoiding, etc., where you will have different type of strategies or algorithms that you might use, and you might need to switch between them with some sort of properly designed logic for the system, okay? Switching for us will be maybe an if-else kind of a statement, but the condition on the if-else should be properly designed to avoid probably fast switching or switching to a mode of operation which might not be safe, right? You can also think about situations where you have constraints. At the end of the day, one of the things I wanted to kind of nail down today is this intention, and I would say good opportunity, to use AI-based control strategies, which essentially based on what is called deep reinforcement learning for control, where you would measure some quantities of your process, here the process on the right, and based on those quantities, you will essentially decide how to control the process. And one way to do that using deep reinforcement learning is to have a pre-established structure, which we call a neural network, which might be deep, where you have some parameters that you need to choose, right? And those parameters need to be chosen in an appropriate manner to guarantee a property of the whole system. And one way to do that is via training, meaning that you're going to explore the space of possibilities or opportunities for the system, and then figure out how to control the system to accomplish a particular goal. And goals could be converging to a particular set point, avoiding a particular obstacle, remaining in a particular safe region, and so on and so forth. The caveat on those systems is that certainly we can actually train based on experiments or numerical simulations, but the question is, how can you now certify, or how can you prove to some degree mathematically that the entire system that you have will satisfy the property that you want? Okay. Now, from a control theoretical viewpoint, for certain classes of systems, which are rather general, you can actually prove those properties analytically using tools from linear, nonlinear systems, and others, like hybrid systems. But the question is, how do you actually prove properties when you pick parameters on this structure? Again, this is a number of functions that are composed with each other, perhaps, which is a neural network, in order to guarantee the property of your system. And the key thing here, in my opinion, is that what the training should give you is a close enough approximation of the behavior you would like to have. Unless you're very lucky or very particular problem that you're working on, you will not get the right answer. You will get a close answer. So the question that pops up right away, in my opinion, is robustness, because you're not going to have, through training, precise convergence to your desired weights, because the structure itself might not actually give you the right approximation of the function that you want. It will give you an approximation that is not exact, but is close enough. So the question is, how can you now guarantee with a close enough approximation of your strategy that you will guarantee a close enough version of your desired property, right? So you want to converge to a set point for cruise control, let's say, you need to settle and be happy with converging to a neighborhood of it, okay? But how do you even guarantee that? And the question is training, right? The key problem there is training. I wanted to start with a problem that I've been fascinated, and I thought that this would be a good starting point for our discussion here, where you have a vehicle, you have a target, you have an obstacle. This is kind of the canonical robotics. You've probably seen this before problem, where you want to go to the target. And right away, as you see at this problem, look at this problem, you look at this and you have, well, I have multiple ways to get there, right? But there are two main ways, right? One way is to go in a clockwise manner, maybe to the left or above the obstacle. Another one is to go in a counterclockwise manner, in like this, you see below the obstacle. And when you see this problem, you're like, okay, this is fine. I will probably have some sort of logic that says if I'm above this line, I go this way. If I'm below this line, I go this way. Everything should be fine. But the question is that a good way to proceed? And the answer is, well, let's solve this problem using a reinforcement learning scheme, right? See what happens, right? So what is a reinforcement learning scheme like giving us? Well, let's say we use something called DQN, which essentially says, what are the actions I should actually use, given the state and given my possible set of actions, to maximize or minimize my cost, whichever option you pick. I would like to pick a cost situation, but minimize my cost or maximize my reward. That's fine. All right, that's how I go. And I fill out this table using exploration of my state and my inputs. And then I figure out a table entry. I build my neural network that encodes that with what we call activation functions here. And then what I can do is to run it for that particular example. Again, simple problem, planar problem, two-dimensional, just an obstacle, one target. What is the big deal? The one thing that you do is, after running this scheme, you look at the inputs that, let's say, the vertical motion only, okay? This is the input to move up or down, which is the most important thing, because you can have a constant input towards the right, and then all you want to do is to move up or down, right? That's the main decision variable. And one thing that you realize is that right behind the obstacle, this is where the target is right here, right behind the obstacle, the input value changes dramatically in that region. It goes from 1, which is going to take you over towards the clockwise direction, to -1, which will take you over the counterclockwise direction. So when you look at this, you say, okay, well, my strategy or my policy is doing something that is not continuous, meaning this change in direction dramatically. It makes a lot of sense. That's what the nature is. If you're a driver, you're probably going to do the same. But from a point of view of control, what's going to happen is that I can induce noise in these measurements, and now I can have problems with my motion. And this little cartoon is just showing that if I start my vehicle right in the opposite side of where my target would be, and I add a little bit of noise, the vehicle could think that even though I'm above the line, the measurement is below the line, and it can actually create a motion that goes down, and the opposite can happen. And then the vehicle could actually, if you don't do anything about it, again, it's like an academic situation, you can actually get this collision. So what is the takeaway here? Well, why do we do feedback control? To compensate and stabilize and accomplish our goals in the presence of perturbations. You can actually show that this perturbation here can be arbitrarily small because you can always find an initial condition that is arbitrarily close to that line because of this continuity of the policy that RL gave you. So this for us was an open our eyes and said, look, if you solve these problems, again, just one vehicle, one target, one obstacle. If you have multiple of these, it gets worse. I'll show you a little more about that. Arbitrary small amount of noise can create this kind of bad behavior. We can call it crash. You can call it lack of performance because maybe you can detect that you're not making progress and then all of a sudden you say, okay, let's change the strategy. But at the end of the day, what happens is there's a topological obstruction in the system. There is a manifold structure, which I won't get into the details, that prevents you from having a global result that is robust to small perturbations. So you need to settle on something that is just local. And we don't want that. Because we want systems to work globally to some degree, at least regionally. And we want these systems to interact with each other. And this is, I guess, a nice description from some collaborators at NASA that actually create this vision of having multi-systems interacting in congested environments with obstacles, with changes of the structure very rapidly. So having said that, my question has been over the past couple of years trying to understand is how do we actually work with controllers that are certified and controllers that might not be certified, okay? I will call the RL controller an uncertified controller, even though it's maybe certified numerically, but only to some degree, and with some caveats, as we saw right here. So how do we actually can cope with that lack of formal guarantees, okay? We are not going to get into much detail of this, but are there Lyapunov functions? Are there barrier functions? Are there cost functions that will give me optimality and convergence? And then how do you actually learn these policies in a way that is going to scale? That's a totally different issue I'm not going to get into. And then something that we have a project I'll mention in a moment is how computationally feasible are these strategies, right? Because if you're going to do reinforcement learning, if you need to explore the entire region of operation, it doesn't need to be unbounded, then you need to grid the space. And then you also need to figure out how to determine the value of the policy. That typically happens offline. When you deploy this online, things change naturally online. And how do you cope with that? So just a little segue, we're working on this project, and this involves a number of PIs, including people from UC Berkeley, Boulder, Vanderbilt, and UPenn. Of course, Santa Cruz, we are the lead. It's a large National Science Foundation Cyber Physical Systems project where we're looking at ways to design the systems so that they're computationally efficient. And by systems, I mean not only the feedback controllers, but also the computer architecture, because we strongly believe that this should be designed in a joint manner. So in other words, you don't throw an algorithm to a particular computer that someone gave you because that was a convenient choice or the de facto choice. You should actually pick both at the same time. And maybe you agree that when you buy something like an iPhone that works really well for maybe until the next update, it's because the software and the hardware have been optimized to each other. And then as software evolves, then this hardware falls behind. So that's the idea. So we have that interest on how to actually compute, and reinforcement learning doesn't really fit here. What does really work well is model predictive control. And model predictive control does a good job because you can actually optimize and adjust your inputs in real time based on the optimization result that you get, and you do that in a recursive manner. One technique that I'm going to bring here, which is something that comes very naturally, and I show you that hybrid automata with multiple modes of operation, is what's called supervisory control, which supervisory control is generally a solution to solving a difficult problem using the divide and conquer approach. Essentially, let's say you want to park your car. So you don't solve the control problem from your house to the car, right? You solve it into pieces. Okay, I'm going to get onto the road. I'm going to get into the parking spot, and then I'm going to get closer to the parking spot, and then I'm going to park. So you have this kind of breakdown, hierarchical approach to solving the control problem. This emerges in applications where there are obstacles, applications where there are nonlinear dynamics. This is a canonical pendulum system, but now with three links, where, if you have three links, now it's going to be kind of hard to swing them because you have very intertwined nonlinear dynamics. However, you can decide a controller that will bring the links to the bottom, removes all the energy. Once all the energy is removed, you can now pump energy into the system. And that's what I have right now. As the energy pumps, the unstable modes don't get excited. And then when you get close to the top, then you get another controller or a strategy that will actually stabilize it there. So you can take this idea to other applications. This is an aerial vehicle application similar to the parking problem, where you take it close to the trajectory you want to follow. This is an underactuated rigid body. And then once you get there with the right conditions and the right states, then you can actually follow this trajectory. Now, when you start looking at orientation, as I said, it's a manifold structure. This is a spatial Euclidean, as I mentioned, 3. And now you have the topological obstruction that I mentioned. You need to solve this in a way that guarantees global asymptotic stability or global tracking in this case, and with robustness. So those are the type of things that you can solve, and we've been doing this over the years. Some of the features that you can actually incorporate into this supervisory control is not only the dynamics of the system and the dynamics of the traditional controller, let's say PID, model predicted control, and so on, but you can also incorporate logic. And that could be via logic variables, it could be via timers that will keep track of when things occur and when things should occur among given deadlines, and memory states of the system. So there are a lot of situations, and the vehicle problem is one of those that fall there, and we solve it without reinforcement learning in the past. So the result of control is what we call is a hybrid system, because now it has these continuous evolving variables like the physics of the system, but also have these logic and not necessarily a standard variable like memory states and timers that might be triggered and reset according to certain conditions within the control algorithm. Okay, and I'll tell you a little more about that in case you're interested and you want to dive into more of the hybrid systems results that we have. So with that short introduction, I'd like to go into how we solve the obstacle avoidance problem using a hybrid switching scheme. And then I'll dive into some of the details of the general supervisory scheme that I was thinking of at the beginning of this talk, which is where now you can monitor your control algorithm that is not certified using a certified baseline controller. All right, so we already know that these situations have issues with noise. We already kind of looked into the literature and understood some of the techniques that are out there for coping with robustness in reinforcement learning schemes. There's quite a bit of work on adversarial attacks, analysis on worst case scenario of reinforcement learning settings, and then safety with control variable functions. The catch is that, especially because it's a discrete time, is that none of these works focus on the topological abstractions emerging on these situations that I mentioned, in particular the vehicle problem or pendulum problems or rigid body problems or aircraft problems where you have manifold structures. So again, as I said, these emerge in vehicles like that, emerge in set stabilization on circles where you have another topological abstraction there if you want to stabilize to this point. As I mentioned earlier, spatial orthogonal, spatial Euclidean, unit quaternion, all these situations where you start looking at orientation, which are naturally emerging in rigid body models, which is something that we typically work on, then there is not a lot there to be done. So how do we go about it? All right. So our goal is to guarantee this convergence to the target point in the obstacle with some safety, meaning we are not going to hit the obstacle, okay? Okay, so the problems are the topology. We need some sort of logic in order to overcome that fragility that emerged from the discontinuities. And we also need to have some sort of logic, right? So I'm selling you a hybrid automata that's been around for, I would say, 20, 30 years now. But the idea is that, well, this is a very powerful tool because now you can actually use different modes of operation. And the idea will be that we're going to have two modes of operation, one to go up, the other one to go down, but the switching is going to be done in the right way. So that's the bottom line. So how does this strategy go? We call the strategy hysteresis RL, and we published this in the Journal of Reinforcement Learning a year ago. All right, so how do we go? So first of all, what we would like to do is to be compatible with the standard RL. Okay, so you can actually start running your control policy. So you run your favorite RL, let's say DQM, PPO, whichever you want, you run that, okay? All right, so we run it. That's what we got. I mentioned that there are issues. Don't worry about it for now. You're gonna fix those issues. So this is the policy that you obtain, or the feedback law that you obtain, okay? Now what we can do is to identify the critical points. Okay, so search for the critical points. This is not a trivial task, but you can find the critical points from the, what is called the best value of the problem, which is the value function. And you can find these points of non-differentiability that are marked here in dashed red. And those are the critical points. This is a numerical search. You don't have the value function analytically. You have a neural network that describes the approximation of the value function, but you don't have the analytical version. But you can find nearby critical points. And they say, okay, this is my bad set of points. All right. Now what I'm going to do is to put balls around those bad set of points. And certainly the target point is one of those, but we're going to get rid of that one because that's where we want to go. We clean the target, and we define these boundary regions, this blue M0 and this green M1, okay? So those are essentially dividing the space into pieces. And then what I do is to essentially take a convex hull of all these points. So there they are, these S1, S2, S3 are all giving me these red regions that might be marked as bad points. And now I create these regions, which actually they are here. Okay, all right. So now I add these sets. And again, this all works in a compact set because RL works in compact domains, otherwise you wouldn't be able to train. So now I have my blue region, which is from the axis to the top, and then I have my red regions. And now I think about this and as a subset of my whole state space, which is the box, right? And now what I can do is to train my system only on that region. And if I train reinforcement on, let's say, PPO on that region, what's going to happen is that since it cannot go down because there is no feasibility, it's going to always go up. Okay? So that's what these sets are doing here. And I can do the same for the green and the red region. Okay? Now remember, this red region is not too bad because that's where we're going to go. The red region that is bad is on the other side. But again, the new training that gives me two different policies is going to be without any topological obstruction because I brought down the space. And it's not going to give me any points that are critical. And then it's going to go all the way down. Again, this is for a simple vehicle model. If you start adding higher dimensions, then this picture become higher dimensions, and that's not trivial. All right, so now when you train it on this new area, the blue plus the red, you get this new policy, and all the trajectories are going to go that way. And then when you train it with the green and the red area, the union, then you get this other policy. So they have two policies. The only catch here is that the policies, operation regions, overlap, right? So the question is, if I am on this in beginning of the blue trajectory described with this path, I could go this way, but I could go also this other way below, okay? Now, what's going to give us determinism is a logic variable. So I'm going to attach a logic variable to this policy in this region, let's say equal to 0, q equal to 0, that's my logic variable. And I'm going to attach another value to this one, q equal 1. And the only time I switch between them is if I hit the boundary of the red at the top. Okay, so now I don't have this uncertainty. So again, I'm kind of giving away what happens here, but this is what we actually do. We implement a hysteresis switching mechanisms through hybrid control that will allow me to now have this switching to be robust to small noise. Okay, and the price you pay is that you might be on the top part and you might go down. So you lack performance. Again, there is no free lunch. There's always some sort of, if you gain something, you lose something else. And in this case, you lose performance by gaining robustness. All right, so what are the values, 0 and 1, to determine the active policy? And there are the policies that already kind of give you the intuition. And now we can actually have a switching logic where it's very simple, right? if I am in this blue region, which is this whole thing, the red and the blue, then keep Q equals 0. If I'm in the green region and the red, keep Q equal 1. However, if I hit the boundary, if I start going on this Y region, when I'm with Q equal to 0, I switch to Q equal to 1. And that gives you a jump on your state component Q. And that's a source of hybrid behavior, which is very simple, but it's a source of hybrid behavior. And the same, we can do the opposite. If I'm in the Q equal to 1, which is green and red, but I hit the white part, then I switch to Q equal to 2. And that gives me essentially the logic. Now, the question is, how do we put all this together into a model that we can analyze, right? Because we would like to say something about the entire interconnection of my system. All right, so that's where we're going to get, and that's just a summary, that's where we're going to get to hybrid dynamical systems, okay? All right, so the assumption here that I'm making is that you're somewhat familiar with continuous time systems, differential equations in state space, and discrete time models. Like Q plus equal to 1 is a discrete time model, right? At an event, Q changes from 0 to 1 or from 1 to 0. So the assumption is not that big, so you can come with me. And this is what I teach in my graduate course on hybrid systems to my students. And the idea is that now I can think of this particular vehicle control problem that I just outlined a solution for. I can think about being part of a family of dynamical models that are hybrid, okay? All right, so what's going on here? This is essentially a model of a hybrid system where the key variables of my system are now called X. This includes position, velocity, logic variables, timers, memory states that evolve continuously according to this differential equation, okay? We could have an input here. I'm not adding that because we're thinking about the situation of closed loop, but we can add an input here if you have that in your model. And then every time that there is an event, we're going to have a reset of my state. It's going to go from Q equals 0 to Q equals 1. The physics variable, like the position of the vehicle, is not going to change, right? So that component of this reset is going to be the identity. Nothing changes. However, I'm going to capture that with a function, call it G, okay? The key question here is, when do I allow my system state to evolve continuously or discretely? And that's where the if analysis, right? So an if analysis is no more than a set, right? If I have X greater or equal than 1, right, on the line, that means the 1 and beyond line, semi-line, right? And if I say X less than 1, well, okay, that will be when the jumps occur or the resets occur, that will be another set, right? So you can build this as sets of your region of operation, or what we call the state space. So that's the idea. So essentially, you can think about now behavior of the system to be a variable X, maybe high dimensional, that evolves continuously over time, as long as it's in this region called the flow set C. And whenever it hits this set D, you might have a reset. And the reset is going to be given by this function here. And then after that, the new value of X might be in C or in D. And then you can continue that logic over and over, okay? So this F is a flow set, this G is a jump map, and this D is a jump set, and this C is the flow set, okay? And then you can think about what we call, I'll get into the inclusion in a moment, time. So what do we call time here? Well, there is a combination of continuous and discrete, so I could use T to parameterize flow, continuous evolution, and I can use J, or you can use K as well for discrete time, but I didn't want to confuse with discretization. J is essentially the number of events that my system takes, okay? So now I can think about let's say, an initial condition to this initial value problem with hybrid dynamics that starts at a particular initial state and evolves continuously for T1 seconds. T1 larger than 0, that's an interval of flow with no jumps. There is a jump at T1, and there is flow from T1 to T2, and the jump counter goes from 0 to 1. And you can keep this over and over. So this is what we call the trajectories, or more mathematically speaking, solutions to the differential discrete, in other words, hybrid system, okay? All right, so how do we write this down? Okay, this is a trajectory of my system for a solution. It evolves continuously up to T1, then it jumps. It may be that it jumps again because it's back to the jump set, and then it flows and it jumps and so on. But now you can see where these trajectories are defined is not just ordinary time t. It's ordinary time t combined with number of events or number of jumps. And the ordinary time segment indexed by j keeps going and creates your solution. We wrote about this a number of things. We have a book on hybrid dynamical systems and a book on hybrid feedback control that uses ideas of dynamics, so proves asymptotic stability, safety, some optimality, and then later we did work on the control, how to design control algorithms that are actually naturally hybrid. One thing that we have is a MATLAB toolbox to actually simulate these systems, because as soon as you start adding events into your system, simulating them is not a trivial task, right? And the question is, can I argue that my simulations are going to be representative of the true system, right? Which is what simulation should be about. And that is something that we've been working over the years with people at MATLAB. With that, now we can go back to the problem and the solution that I mentioned, and I can instantiate that framework. So if you missed something there, hopefully it becomes clear now, where I have now, this will be my flow set for q equals 0, okay? And this will be my flow set for q equals 1, right? Where the system can evolve continuously. And then the boundaries will be the jump. So what is my state X of this larger framework model? It will be the position of the vehicle and the logic variable. This is the region of operation of my vehicle Z, and this 0, 1 is the logic variable values. And then these are the dynamics of my vehicle, this FP, that is given by the policy at the current Q. Okay, so if Q is equal to 0, this will run with policy pi 0. If Q is equal to 1, it will run with policy pi 1. And that will be the flow part. And the flow set will be where the regions are, the blue and the red with Q equals 0, the green and the red with Q equal 1, okay? Now I can take the same approach for the jump logic. I was talking about these regions to be in the Y regions. This essentially is the complement of what I have minus a closure of the set, sorry. And then that will give me essentially the logic for the jump set. But more interestingly, the jumps themselves will only reset the variable Q. If it is 0, it's going to go to 1. If it is 1, it's going to go to 0. And that is as simple as writing 1 minus Q, because 1 minus Q evaluates or flips the value of Q from 0 to 1 and 1 to 0. And then you realize, oh, this is a nice function, even though it looks like an esoteric logic, but it's a nice continuous function. Having said that, then you can write down the full closed loop system in the hybrid framework that I mentioned earlier. And this will be the object that you will look at. And then the question is, what can I prove about this object? What can I say about the solution to this system? Okay. So for certain choices, so dynamics being point mass, the policies being continuous that can be imposed through training and the choice of the neural network, these sets being closed, which are by construction, and the interior of the obstacle being properly chosen, then we can show that for this closed loop system, you always have a trajectory, right? Because there is something that you might be aware of, but certainly is the only thing about it when you're dealing with these problems. Let's say you have a timer, and the timer is evolving as the derivative of the timer equal to 1, which is time, right? And then you say, okay, I want the timer to remain between 0 and 10. When the timer hits 10, then it's over, right? The timer cannot evolve anymore. So unless you reset it back to 0, your trajectory ends when it reaches the value 10, right? So existence of solutions is something that we take for granted for linear and nonlinear systems with the right assumptions, but for these systems with logic, you can get into a deadlock condition that you cannot evolve anymore. So guaranteeing that exist solutions and that they are not switching arbitrarily fast, which is what is called Zeno, is important. And then more interestingly, how many jumps do I have? Well, I have no more than 2 jumps because I might initialize my system incorrectly, have an initial jump to put it in the right initial condition, and then I might have another jump because I'm in the boundary of a jump set. So I have no more than 2 jumps. And then more importantly, I have convergence to this set, which is the target with some logic variable. I don't know if it's going to be 0 or 1, as long as the noise is small enough. All right, so I don't have this issue or fragility relative to the noise being large in some sort of a critical point set that I described earlier. And this is what we presented at that journal. Other examples emerge naturally in robotics. This is, as I mentioned, this is a situation of a planar orientation. So a good way to avoid the periodicity of an angle is to think about the orientation of a vehicle as a point on a circle, right? Because the point on a circle is going to always give you the angle, but then you don't need to worry about is it 0 to 360 and what happened at 360 or what happened at 180 minus 180. Anyhow, but you have that topological abstraction because if you want to have that no matter where your orientation starts, you want to converge to this, let's say, desired zero orientation, which is an arbitrary chosen, but it could be any orientation, then you're going to have a situation on the other side that gives you, well, if I'm here and I want to go there, I'm going to go this way, green, if I'm a little bit low, and if I'm a little bit above, I'm going to go this way. So you have the same issue, right? That's why, again, this is a manifold of dimension 2 that gives you trouble. And that trouble can be overcome, or you can see it from PPO. This is what PPO gives you. Actually, PPO gives you another discontinuous feedback law. You can exploit that. But if you compare the PPO with the hybrid, as you can see, there's a PPO trajectory here that stays there, but all the hybrid trajectories that are in blue leave that antipodal point. Simple but efficient. And then the vehicle problem that I already mentioned to you, you can now run simulations and you can see that with a small noise, actually very randomly selected noise, you can actually get stuck there. And if you pick it always in a periodic manner, you can get stuck there forever, while the blue trajectory has this behavior, which is hybrid. However, as I mentioned earlier, there is no free performance because I'm starting from that very point below the line and I'm going over. So the shortest path is this way, but I don't do that. Again, I have to pay the price. And this is an experiment that we run in my lab. This is the DQM policy. And as you see, the vehicle gets stuck there. It's just being around a neighborhood of the obstacle, and our hybrid RL, which uses DQM with the logic, it actually converges. Not a problem. Again, this gets more interesting, maybe, when you start looking at real-world situations where now the information comes from a bird's eye view, and the vehicle model becomes maybe a more sophisticated model, like the planar position plus orientation, which is called the Dubin's model. And now you have not all observations, you have error observations, and you can get those from images. And then you are going to have noise, which is coming from the images. So you have regional information only, you have also measurement noise, we tackle that as well. Another situation, you have multiple obstacles, right? So in this air mobility solution, you have multiple of those. And if you do suddenly apply RL without thinking about that, you might have some trajectories that converge, but some other ones that get stuck. As you see right there, all those ones get stuck there. And that's a problem. However, we can do hybrid RL with a multiple obstacle, and now you can have all of them converge. Again, the price being paid, lose a little bit of performance, but that loss of performance can be calibrated or chosen by the parameters. So this is essentially what happens. So it's a trade-off between performance and robustness. I said it multiple times, but I wanted to say it again, but that's something we can tune, okay? If you know the size of your noise, then you can say roughly how much performance you're going to lose, and that's useful. You can apply these to situations that are more of a competition. This is a capture the flag situation. Another you can think of is your scheme will be a scheme that introduces noise in the RL scheme that makes it stack behind obstacles, and then you can catch the flag. So this cartoon here is showing that. The blue is high RL, and right there is introducing some noise. The other one is introducing the same noise, but it's not affecting it. It got it stuck there, it grabbed the flag, and then luckily it goes home. The other guy didn't catch it. So you can exploit that vulnerability if you know there exists one. You just need to know what it is and get advantage of that. And this is a situation where now we're looking at higher dimensions. This is in collaboration with the AFRL lab in Destin and Florida. And we're working on how to actually test these 3D situations. They have a large motion capture area, but I'm excited about other extensions and also validations of this. We also have a timer base of this. I'm not gonna talk about this too much, but you can actually, as you see right here, if you don't do hybrid, you get this kind of behavior, but once you start doing the hybrid switching, you get this nice convergence pattern. All of them converge, while when you don't do hybrid, some of them converge, some others get stuck. This is multiple vehicles, multiple obstacles. I wanted to get to the last piece, which I will give you an idea, but I think it's an idea that has a lot of potential, and we developed with Paul Wins, who just graduated, and we're very excited about the idea of supervised and simplified controllers, which connects very nicely to what we typically find in the literature of safeguarding. The idea is that I'm going to get a little bit mathematical, but if you have a system that you want to control, let's say a nonlinear control plant, and suppose that you want to guarantee a property star. Suppose that you have a property that you have a controller that gives you that property. Okay. All right. So this is for control theory people. This is a feedback law, which is static, which can be coming from RL. But again, suppose that you have that property induced by that controller. What if you have another controller, call it kappa 1, that gives you some sort of an advantage, but not necessarily certified for that property? Could you opportunistically use that new controller whenever that controller gives you some advantage versus always using the controller that you certified for? And what I'm thinking about here is that suppose that you can solve on the fly a problem that you actually can benefit from data. And then all of a sudden you enrich your model. This function FP is richer, and then you can solve an optimization problem every few units of time, whatever it might be. So when you solve it, you apply it as long as it gives you an advantage. And then when that controller becomes stale and doesn't do any good anymore, you can go back to the original, maybe baseline controller again. Okay, so that could be for stability, that could be for robustness, that could be for optimality. So the idea comes down again to switching. I will switch between something that I know works okay, but it's probably not the best thing in the world, and something that is opportunistic. Maybe I can solve it, maybe I can train it, maybe I can figure it out on the fly. Maybe it takes time to compute, right? And then I can use it when it's ready to compute, and I will switch between those two, okay? So the problem is now is more generic. The design supervisor for the use of kappa 0 and kappa 1, such that you have the property star that was certified by kappa 0, but kappa 1 is preferred over kappa 0, okay? You cannot just apply kappa 0. If kappa 1 is giving you advantage, use it. And then, as always, when we do switching, no challenging happens. Otherwise, it won't be implementable. Okay, so how do we go about it? And one last thing is the property is robust, but I don't have time to get into the details. So let me just show you how we go about it. Imagine that that property star, just for example, we have a few papers on this, is asymptotic stability, okay, of a set of points. Let's say this is a set point for my target for the vehicle, right? Okay, so I build a closed loop system. I call that F0. And now I have a certificate for that. So what a certificate could be, if everything is linear, I have a eigenvalue property, or if it is non-linear, I have a Lyapunov function. Okay, so let's say I have a Lyapunov function for that system. And now I have these properties. If I have a Lyapunov function, I have this positive definiteness and growth conditions, and I have this decrease condition, meaning that my Lyapunov function V0 has a derivative that will be negative so that the function V0 decreases along the evolution of the system. And it will decrease until you get to the desired set. Okay, so this is one way to characterize it, okay? But keep an eye on this V dot, right? Because the V dot is going to be important for us. Because now what I can do is to calculate V dot for the controller kappa 1. Or I can evaluate. If I don't have a closed form expression, I can evaluate my derivative of that function V when I use that input. Okay, and now I'm going to use this as my, and this is a paper that we published, and I'm going to use that V dot as my decision maker, okay? So let me give you a quick example here. I have model predictive control, and I have this controller kappa 0 that is a static standard. But now I want to use model predictive control. And my model predictive control is so good that it's going to give me convergence to 0 in 1 second. So which one of these two you like to use? You want to converge? Well, most likely this one, right? If it doesn't violate the input constraints, you're going to converge to the set point as fast as you can. All right, but what happens if now the model control doesn't compute all the time, or doesn't terminate as fast as you want, right? Well, what's going to happen is that if you keep applying it, because you haven't been able to compute another optimal input here, it's going to give you something like this. And then when you solve it again, it's going to give you the right behavior. So here's the bottom line. Why don't I use this thing and then switch to that so that I can converge faster and stay there? So can we still explore it? The answer is yes. I can essentially use model predictive control for some time. I won't know when I get there. Perhaps maybe I wait a little longer. And when I notice that it's now things are going wrong, safeguarding will trigger and it will give me my convergence by switching to the nominal controller. I can squeeze in again, the model predictive control is right here. There's another model predictive control usage here. And again, I can plug it in and plug it out as needed based on the properties of the system. So that quantity is key. That's a quantity that we would like to follow. And the switching logic, I'm going to skip a little bit some of these conditions, but the switching logic is essentially saying that I will use the certified controller if I don't see a lot of good improvement from the new uncertified controller. So, however, if I have that, I have a good improvement from the uncertified controller, I'm going to switch, right? Okay, so what is it saying? This is saying that if the variation of my V along the evolution of the new controller is small enough, then I'm going to take it. I'm going to take that dive. I'm going to jump. So that's my jump set from 0, certified, to uncertified 1. Otherwise, I will remain in my certified controller. And then I can do the other way around. If I'm using the uncertified controller and I'm doing pretty well, I'm decreasing nicely, then I'm going to stay with it. But if all of a sudden I start getting a lack of decrease, my variation starts becoming more or less negative, more positive or less negative, and very importantly, the value of my V now becomes larger than what it was before, then I will switch. So essentially, I have this safeguarding, which for this simple point mass model gives you kind of idea. Let's say kappa 0 is minus z, kappa 1 is minus c cubed. Minus c cubed gives you a very nice deep decrease towards 0, but eventually it settles. But minus z gives you a very nice long-term decrease. So you would like to use this orange and then the blue, and that's what the algorithm would do. And there goes. So this black one is essentially the best of both worlds, okay? Again, these are not very sophisticated. This is just to make the example, but now you can imagine that if you run something that you say, okay, my computation terminated, can I use it? Well, look at the certificate. And the question is, how do you assign a good certificate, right, to start with for the baseline so you can take most advantage of this? And that's problem dependent, but that's a very important problem to solve, okay? All right, so that's kind of the logic. Again, now you have been exposed to hybrid systems, so you can imagine there's a hybrid closed loop system behind this in the framework of the calligraph H model that I mentioned earlier. Z, which is the plant, doesn't change at jumps, but the Q changes from 0 to 1, 1 to 0 as before. We have this V that is going to be monitoring the value of the Lyapunov function. The state Z evolves according to the closed loop dynamics, and Q is constant unless there is a jump, which is an event. And I can design now the evolution of this V function that a little bit that I won't get into the detail, but this is essentially giving me the trigger. So now I have a closed loop system that I can think about mathematically. And this kappa 0 pops up here. Kappa 1 might pop up here if you have a closed form expression. If you don't, then this will need to be essentially a piece of code, and that's okay. And you can actually say things about this system, okay? I will say that one of the things that we can do is that we can prove that there's a lower bound in between the jump times. That's because of this sigma 1 and sigma 0 that didn't get into detailed functions designed by themselves, give you that. And now we get that this set where we want to converge, let's say the set point for Z and 0 for the V, and whatever Q it might be, it's okay. You get asymptotic stability to that. And then you get some robustness to small perturbations through the assumptions that I mentioned right now in the previous slide. But to get small perturbation and robustness, you get large perturbation is part of current work. I wanted to also mention that the application to this, or well, the application that we've been working on this is this idea of autonomous landing. So we've been working with some of the eVTOL companies. We didn't want to put an eVTOL here because it's very secretive, as you probably know. But this is your favorite Cessna 172 going on a runway and trying to going to land, right? And then here's the idea. Well, you have maybe a good expert on the plane. You hope you have that, right? Maybe it's a synthetic one, but maybe you have a pilot, and that the pilot is going to actually give you this kappa 1. But this is a baseline control is the kappa 0, which might be doing okay, but when there's wind into the situation, then that might not be that good. So this is essentially a trajectory. The blue trajectory is a reference, and the red trajectory is the behavior of the system, trying to convert to this nice glide slope for landing on, this is actually Watsonville runway 20, which is a fun runway. And this is a movie of that, and getting there with a combination of model predictive control and some of the ideas that I mentioned, landing on the third of the runway and getting there and moving forward. And the idea is to actually implement this in a system that we can actually test in the real world and provide guidance to the actual pilot, or maybe implement it in the autonomous system of the pilots of the plane. But this is within something that we're building with several folks here in the Northern California area. Some of the names are listed here, working on what we call California Link, which connects not only the University of California campuses, which have been connected through Citrus, I mentioned earlier, but also through one of the activities that we do with this is Citrus Aviation Prize. I know that William is part of, and maybe others on the call as well. Leighton is part of this, Natasha as well. And we work on trying to create the next generation mobility system for not only the University of California, but also for structures that will use eVTOLs. And as you see here, we cover a number of places. So we cover Moffett, we cover the Watsonville Marina and Hollister, all the way to Merced, and we have a nice region here. This polygon provides a lot of diverse in not only airports, but also weather, air traffic, airspace, and conditions to navigate. So we're very interested in these ideas, and we're looking into a lot of opportunities. We have a few proposals out there, and we're excited about this. And if you're interested about this, please let me know. We're excited to discuss more how we can work together on that. I also have a project on space. That is an Air Force project on safe space operations. Many of the things that we do in control emerge nicely, and actually sometimes are simpler in space because there is no wind. And one thing that is very critical here is actually how do you actually solve problems related to assembly or decommissioning or repairing in space. So it's a multi-role collaboration where there are contacts, there are switches of control, as you can imagine. Hybridity will emerge in the dynamics and also on the solutions to the system. And this is the project that we have. We've been working on docking and space exploration and a lot of interesting things. With that, I know I have a few minutes left, and I wanted to give opportunity for questions. I want to thank you for your attention.
I was just kind of curious. I know that everything that you presented was like, you have controllers, like separate controllers that they have the common goal of reaching some kind of goal. I was kind of curious if you ever considered like contradictory controllers. Like, let's take the obstacle avoiding one, right? Like you solved it. I did too, but right now you have an obstacle and then the goal. But what if you decompose it where there's an obstacle and then another problem where you're trying to just reach a point? So like it's a controller that's like reaching a point and a controller that's avoiding an obstacle. It's like self-contradictory.
Yeah.
So I was kind of curious.
Yeah, right, because I think you want to use those controllers if they will essentially help you in solving the whole problem you want to solve, right? And that's where the supervisory control, which is more general than what I present some instantiations of that, is very useful because you can say, I have a controller that's very good at, as you were saying, taking me to a point, but I also have a controller that's very good at taking me away from obstacles. How can I combine them? So you need to come up with a logic that will say, okay, now you should use the avoidance, or now you should use the go-to controller. And we've done a few of those things, but it's certainly, I would say, it's problem dependent, right? Because now you need to guarantee a property for the system, and you need to use this subset of controllers. The question is, what are the regions, what are the C0, C1, and D0, D1, and so on for each of these modes, right? And yeah, there is a lot of potential for that. I think if it solves a problem, because as I said, supervisor control is a great divide and conquer approach.
Right.
Because now you don't need to solve one algorithm for the whole thing. You break it down, but you need to know how to break it down. And sometimes the break it down itself is part of the design, right?
Yeah. Oh, it's definitely interesting. Yeah, I imagine that it would definitely be the supervisor control, which is kind of interesting. Yeah, I guess it becomes complicated when you're dealing with, like different, maybe contradictory schemas, and then it's like, how do you stitch it all together with like switching rates? You should switch one to another, but although it's kind of
Just yeah, very common.
Right. Well, I want to thank you, Dr. Sanfelice. Then next week's speaker will also be here in person, will be Dr. Alexander Valle, Director of Citrus and the Banatao Institute. And his topic will be LLM approaches for voice ADSB architectures towards a digitalization of ATM operations, prompt engineering, joint embedding, and diffusion models. So we look forward to seeing you in the flesh here next week. Thank you so much.
Thank you.
Thank you.